So, where do fertilizers come from? Uh, this is something that maybe there's some confusion about, maybe there isn't. Let's go through the list here. Potash. Potash is mined from the ground, as you see in this picture. A very tidy cavern that's been carved out of the planet. Potash, basically there's two main sources in the world, Russia and Canada. And Canada has a very large deposit of high quality potash. And potash is, because it's potassium, is one of the key nutrients required for fertilizing crops. And that puts Canada in a very prestigious position as far as feeding the world goes. And the other half being Russia. Russia has its complications, I suppose we're all familiar with that. So potash is mostly found in Saskatchewan and Manitoba, and that is where our source is. Many times there have been companies that have tried to do what we call a hostile takeover with foreign ownership of those mines, and the Canadian government sees it as very strategically critical, so they block those kinds of things. But potash is dug from the ground. It looks like this. It looks kind of like quartz, and it's got some different colors and purities and whatnot in it. And once it's dug out and crushed and screened, it's stacked in massive piles, which, you know, that's just a bonkers pile. What I find fascinating about this picture is that, like, look at the forest is surviving somehow. I don't know how. But anyways, there you go. That's more than a day's worth. Gypsum. This is a key ingredient for supplying calcium for plants. I don't know if you noticed, but if you look carefully, there's a fella standing over here leaning against the crystal. These are massive deposits of gypsum in the ground. Basically calcium sulfite solutions that dried up and left crystals behind in huge caverns underground. There's a huge supply of this around the world. Mexico, the States, Canada, almost every continent has decent gypsum supply. You may or may not be familiar with this, but drywall, which is used to line the walls in our houses, is made up with paper and gypsum. So often it's called gypsum board, but essentially it's gypsum. If you're really desperate to get your hands on a calcium fertilizer for a crop, you could probably crumble up some old drywall and chuck it in. But I don't think I'd recommend that, because there are some binding agents in there, and some of the drywall is moisture resistant, so it's got chemicals in it. But just saying, you know, if you're in a pinch. Here's another impressive photo showing a fella. You wouldn't want to slip there now, I don't think. In a gypsum mine. I don't know if you guys are all too young to remember, but when I was a kid, the first Star Wars movie came out, he had to throw this crystal. He was in, like, somewhere in the North Pole, and he throws this crystal, and it starts this reaction, and giant crystals come out of the ground and create his hideaway. And every time I see this, I think of that. That's completely useless information, and I'm sorry about that. Gypsum comes in less pure forms. This is a less pure form of gypsum. You can see you don't have nice crystals. You've got, like, these sort of wavy patterns in there. Once it's solubilized and recrystallized, it's actually pure. A fair amount of the world's gypsum is in this format. So, phosphate, calcium phosphate. This is a critical fertilizer because it has both calcium and it's got phosphorus. Two important nutrients. Often as an open pit mine. This is like a giant crater in Arizona. The Americans have a bunch of phosphate mines. There are all over the world, but, you know, a lot of our phosphate comes from those mines. Open pit mines have all sorts of challenges. You know, rainwater lands in there and you have to pump it out, and then where do they pump that, because it's kind of got a lot of stuff in it. So these mines, they spend a lot of money and energy on filtering and treating runoff water to prevent pollution. That doesn't mean they're always successful. Another picture of a phosphate mine. whenever I see these pictures, I'm gobsmacked, and I'm embarrassed to be a human. It sounds terrible, but I mean it's just a giant scar on the face of the earth. And at the end of the day, relative to the land mass that this particular phosphate mine is in Arizona, if you looked at it from space, it would be like a pinhead. Not even that. It's a very, very small percentage of the land. Nevertheless, it is a giant crater that we've created. Epsom salts. These are things people buy all day long at the pharmacy to soak their feet in. I don't even know if it works. I mean, it must, but I don't understand how. But hey, I think the act of soaking your feet in warm water probably would be the main benefit in adding salt. Hey, why not? It just makes your feet, the wrinkliness, even more interesting to look at. Anyways, it's mined as a rock called langbeinite. And by the way, these are all these PowerPoints are available in the same folder, so you can actually click on links like this is a link that takes you to the rock. I can't do that when I'm recording. For some reason, it blocks hyperlinks in the document. But anyways, it's magnesium, which is a critical element, and sulfur or sulfate, which is also, it's just a simple salt of that. We use a lot of Epsom salts in fertilizer. And this is what a typical Epsom salt mine would look like underground. These mines are anywhere from 100 meters to 3 kilometers down. I mean, that's far. Going down, I mean, take a coffee. Nitrogen, here's the interesting one. So up till now, all the nutrients you'll notice are mined from the ground, whether it's an open pit mine or a deep mine. Where nitrogen is actually a petroleum product. It is made directly from oil or natural gas. I'm not going to ask you how this process works, by the way. Like, oh, did the compressors? No, that's not the point. The point here is just to remember that nitrogen is a petroleum product. And as a result, nitrogen is probably one of the biggest variables when it comes to buying fertilizer as far as cost is concerned. Because basically as the price of oil fluctuates, the price of fertilizer fluctuates. And I know this firsthand from when I had my greenhouse, where if we were buying a pallet of 2820, it would fluctuate anywhere from $28 a bag to $65 a bag. Now that is huge. That's a major fluctuation. And when you're buying fertilizer and it's impacting your cost of production, with that kind of variability, you really have to have an idea of how much you're using and work some buffer space into quoting your prices if you're selling something. But it is made from mostly natural gas. This is a natural gas plant that's making ammonium fertilizer. Wouldn't love to have that behind your house? Sheesh. So let's look at this. So traditional fertilizers, these are ones you see at the college, triple 20 and 2820. They are all what we call inorganic salts. I will cover this in another lesson or remind you, but inorganic, first of all, the term organic, I know in a lot of your minds brings, images of a mule pulling a plow through the dirt and feeding your crops manure. But organic, the original word organic, is actually a chemical term. And when it's inorganic, it means it's a elemental salt. So two elements that are in the periodic table that are attached together by a charge. So calcium nitrate right here, or potassium sulfate. So those are inorganic salts. When we talk about organic molecules, we're talking about chemicals that have carbon in them. They're more complicated chemicals. They're still synthetic or naturally produced, both, but they are what we call organic as long as they have carbon as part of the molecule. So now, as it turns out, a lot of organic fertilizers have carbon in them, so it works. And I think they kind of stole the term. If you go way back to the early days of the organic movement. They stole that term from chemistry, and I'm still bitter. But anyways, here's the fact. Inorganic fertilizers are non-renewable, right? That means that once we've used them, it's actually, I shouldn't say they're non-renewable, because technically, if you're willing to be patient and wait a few billion years, those atoms will eventually redeposit in the crust of the planet. But you and I don't know, I'd be really bald by the time that happened. But so effectively, it's non-renewable. But the only way we could actually say it's truly non-renewable would be if we take a bunch of those salts, pack them into a rocket, and launch them off the planet. Then they're no longer going to be part of our nutrient cycling on the planet. But from a human lifespan perspective, essentially non-renewable. Which does beg the question, when we go to Mars, those elements that we take away are now gone. So that's a whole new perspective on renewable. Anyways, so potash, gypsum, phosphorite, and Epsom salts, these are all extracted from the ground, okay? I can tell you that on quizzes, which we have often, and on the midterm and finals, I usually ask the question, which of the following is not mined from the ground? And of course, you're going to answer nitrogen, right? Because it's made from petroleum products. It's not mined, per se. Never mind the detail person that says, yeah, but the tar sands are mined. Okay, let's just say it's from oil, okay? So what are the nutrients needed for in a plant, right? This is a really interesting section, and I think it hopefully makes some sense. We're all familiar with things like DNA. RNA is basically a message from the DNA that tells the body how to make proteins. So both DNA and RNA need lots of nitrogen and phosphorus in order to be made. So if your plant doesn't have enough phosphorus, it can't even make DNA. And one of the fundamental parts of a cell dividing, or what we call plant growth, is the ability to make more DNA. So if you're phosphorus limited, plants tend to be really stunted because they can't make new cells, and they're stressed out, so they're purple. Protein, we know we all need protein. We also know that plants don't have a ton of protein. I mean, they obviously have some. I mean, you look at a cow, it's pretty big. It didn't pull that out of the air. It just ate a lot of grass. But yeah, nitrogen, sulfur, and iron are needed to make protein. So once again, you see nitrogen, a common one, right? Common. I can't really draw with a mouse. And then uniquely, sulfur and iron are involved in making a lot of proteins. By the way, this should be obvious. You maybe say, but Derek, you're not mentioning the others. Well, let's face it, carbon, hydrogen, and oxygen all come from the atmosphere. CO2 and water. So obviously those are not elements we need to concern ourselves today. Now, carbon we can supply as CO2 in a greenhouse, so for sure it does. It is considered a nutrient actually, but we're staying out of that because this doesn't fit with us right now. Lipids. Lipids, some of you may or may not be familiar with this term. Lipids are basically a cell membrane. They're part of that. And cell membranes we have as humans, plants have the same thing. Those lipids, which are really important for creating a layer to filter what goes in and out of the cell, those lipids require nitrogen, phosphorus, potassium, calcium, and even sodium. That might be of interest to some of you because you might think, oh, plants shouldn't have any sodium. Well, that's not true. We need it. Just like, some might say, oh, you shouldn't eat fluoride, it's bad for you. Well, that's not true, because if you don't have fluoride in your diet, then your teeth fall apart. And then people say, oh, but fluoride is synthetic. No, it's not. If you eat enough fruit and vegetables in your diet, you actually get enough fluoride because plants take it up. But if you don't have enough fruit and vegetables in your diet, your teeth get weak because you don't have enough fluoride. So we add fluoride to toothpaste, and some cities add it to their water to help people have strong teeth. So not everything is bad. It's usually just, the quantity is something you got to watch, right? Chlorophyll, we should be familiar with what that is. Nitrogen and magnesium. There's actually 4 nitrogens and 1 magnesium in the center of every chlorophyll. And you need a lot. If you don't have enough nitrogen or magnesium, your plant goes yellow because it can't make chlorophyll. And then ATP, this is one that some of you may be familiar with, some may not. This is a small molecule that acts like a battery. It's sort of like a way of transferring energy. And ATP is like, I call it the currency. So if you don't have any ATP, nothing happens. It's kind of like if you go out for dinner and you don't have your credit card or your debit card and you don't have cash, nothing happens. So ATP is involved in every chemical reaction just about that goes on in a plant and an animal. And if you don't have enough nitrogen and phosphorus, specifically phosphorus, because the T stands for triphosphorus. If you don't have enough phosphorus, again, the plant stunts, just like if you don't have enough DNA. The plant ends up really small and very stressed because, hey, it can't pay its bills. Typical things we see, this is just a longer detailed list. You can look at it. Vitamins, this is interesting. Vitamins are often supplemented in basically hydroponics, because we're pushing the growth rate of the plant so much that they can't always make their own vitamins necessarily. So we supplement. We do this a lot, especially in tissue culture. You know, we add certain elements that take a lot of energy for plants to produce. Particularly in the early growing stages of plants, we'll supplement with vitamins. But you won't see that very often in commercial fertilizer. That's pretty specialized. Obviously, carbon source, that's CO2. We talked about proteins and DNA. Potassium is involved in osmotic regulation. If you remember from Plant Science 1, osmosis, that's the act of cells expanding and contracting. How a plant stands up, it has turgid pressure, or if it wilts. Calcium is used to strengthen cell walls because it's so sticky, it kind of cross-links everything. Magnesium, fluoride, these are kind of reviewing these a little bit. And then there's what we call cofactors for enzymes, manganese, cobalt, copper, zinc. I mentioned these ones down here because a lot of times when people are looking at what goes into making fertilizer, they're like, oh man, there's all these chemicals. You need them all. If you don't have these metals, we don't have what are called cofactors, and enzymes might not function. And if you don't have an enzyme, maybe you don't have a vitamin, and it actually impacts the nutritional quality of the produce you're growing. And there's plenty of evidence, and this is something that goes contrary to what you'll hear on the internet. A hydroponic produced farm has such tight control over the nutrition of their crops that they rarely have deficiencies because they are at peak product efficiency. A typical greenhouse will send their water out for analysis once a week. Where if you're growing in outdoor soil, it's very common for soils to have very different chemical properties, and more often than not, they're deficient. And most organic farmers that I know of don't send their soil out for a weekly analysis to see what's going on. In fact, very few send out for an analysis. They just start doing sort of whatever it is they do. And in different parts of the world, this actually is a real problem. Where minerals are deficient in the soils, and when people eat the produce from those soils, they end up chronically deficient. We see that in the formation of vitamins like keratin. There's issues in Southern Asia with blindness because the soil is deficient for certain minerals. In North America, our soil tends to be a bit low on the element iodine. And that is why they iodize salt, which basically means they add a trace amount of iodine in table salt to make sure that our population has enough iodine. If you don't have enough iodine, your body starts to malfunction. Specifically, your thyroid gland doesn't function properly. And then you have all sorts of metabolic disorders. This is actually, in the medical circle, kind of a bit of a concern because the general public has taken so fondly to organic salts or Himalayan salts or whatever salt you want to call it that are not iodized, and there's some concern that there may be thyroid problems cropping up because people have gone away from that. They probably never understood why it was done in the first place. Okay, so this is just an example of an enzyme and how nitrogen and iron play a role. I will not ask you to memorize this, but nitrogenase is an important enzyme for plants. And it basically takes atmospheric nitrogen and converts it to ammonia, right? And eventually moves it into the formation of nitrate for plants to use. And if you look at it, it has MO is molybdenum and iron. There's iron over here. There's molybdenum and iron again here. There's phosphorus here. There's sulfur here and more iron, and then more iron here. And that just gives you an example of how many metals are involved in the making of one particular enzyme. So if you don't have enough iron, molybdenum, phosphorus, and sulfur, your plant can't make enough nitrogenase. It actually struggles to move and process nitrogen from the soil, and your yields go down. The plant becomes weak. It's more susceptible to insects and disease. Looking at chlorophyll, we can see right away here, look, there's 4 nitrogens in the center of this heme ring that holds the magnesium. And magnesium is where all the magic happens. This is where we split water. So you got your H2O, oh, this is hard. And it comes here and split into hydrogen, to 2 times, and oxygen. Actually, this should be 2, and this should be 4. If you want to balance it. But it doesn't matter. Anyways, the point is you need magnesium and nitrogen in order to make chlorophyll. So if your plant doesn't have enough of either, you lose chlorophyll, your plant starts to become a lighter green. A lot of commercial farmers have a chlorophyll meter that they go around and they can clamp onto a leaf. It actually measures the amount of chlorophyll in a typical leaf. And they have expectations or benchmarks for how much chlorophyll there should be. If they're not at that benchmark, they know they have to address their nutrition in their crops. Time for some chemistry. Okay, so what do we mean by salts, right? So with salts, it means that just like table salt, you have a crystal in your, you take a pinch of salt, you got white crystals in your hands. That's got a sodium and a chloride. In this case, it's calcium and a nitrate stuck together. But in table salt, it would be a sodium and a chloride. When you add them to water, they undergo dissociation, right? That's like, you're breaking up with your boyfriend. They split. And they become their own entity. So calcium floats around by itself and nitrate floats around by itself. So that's dissociation. So how do we know how much fertilizer is in irrigation water? Now you probably have touched on this already. We did a little bit in plant science too, so I'm going to review this just a little bit, make sure we're all up to speed. And how do we measure how much fertilizer? Well, we see how much electricity flows through the nutrient solution, right? So we call that electrical conductivity. So you have all those fancy EC meters, right? So if you have salts that are dissociated in your water, they have a charge, say a plus and a minus. When you send electricity through the water, and you collect it at the other side, it can only flow as quickly as there are, basically think of these as like cab drivers. If you've only got 2 cab drivers in the city, it takes a long time to move a lot of people across from one side to the other. But when you have lots of ions floating in your solution, it's like having tons of Uber drivers and boom, huge amounts of electricity flow and you get this high EC. Okay, that's how it works. Each ion shuttles an electron over or carries a positive charge back. And that's how the electricity flows. So that's an EC meter. We apply a small battery charge to 2 cathode and an anode, and the salts move. I'm not going to ask you which way they go because who cares? A little history here. This guy, Werner von Siemens, he basically invented this whole science of tracking how electricity flows through a solution. And so oftentimes we use the term millisiemens, which is what, or microsiemens. Typically we use millisiemens in horticulture. So this EC of 1.2, the unit is actually millisiemens per centimeter. The The centimeter is the distance between the two electrodes, if you were curious. And typically, from the real world, an EC of 1.2 is on the low end, and an EC of 3 is on the high end. Now, I should clarify again, even though we've covered this in Plant Science 2, but these EC values you take with a pen. You always take a background reading and then subtract, all right? So if you're using deionized water, then fine, you can take the reading and be 0. But if you're using city water, you want to measure the EC of the city water, and then whatever that value is, subtract that from the EC you're getting in your pour through, okay? Just FYI. So one of the limitations of electrical conductivity is that it measures all salts. It's not specific. You don't know what's in there, you just know how much charge it can carry. It's not what we call ion specific. Now I have a couple of ion specific probes at the college. I'll admit they're real cranky and it's hard to calibrate them, but we're going to play with them when we have labs this term. So important to measure, EC is not specific. It measures all salts, okay? All right, after EC, we talk about pH, right? And again, review from Plant Science 2, but we got to get into this early. Protons are acid. Basically, an acid is a bunch of protons. And so when you look at water, just looking at normal water, it's always in a state of, as we know, H2O, and splitting up into hydroxyls and protons. And normally this is at equilibrium, which means there's equal amounts, which means we have a pH of 7. If something were to impact the water and it shifts to having a lot less of the water and a lot more of the protons, it becomes pH less than 7. So when we have lots of protons, we have a lower pH. When you have lots of hydroxyls, we have a high pH, right? It goes up, greater than 7. So we don't often talk about pOH, we always talk about pH. But technically, pH, this part, is a direct measure of protons. I'm really making a mess of this slide. Okay, clean. So that's the basis for pH. And alkalinity is something that if you have a pool, or if any of you have ever had a pool, always, oh, we got to make sure there's enough alkalinity. That's true, because alkalinity is basically this chemical called bicarbonate. You've used it before. If you've ever baked cookies, we put baking soda in, which is basically sodium bicarbonate. Although typically in horticulture we use potassium bicarbonate if we're going to use it. But bicarbonates actually gobble up like Pac-Man. Say, pretend this is Pac-Man. They gobble up protons, which means they eat up acid. So that helps raise the pH. Why are bicarbonates so important? Because they help buffer the water to keep it at a better pH. If we have just a whole bunch of protons and they start taking things apart, pH can continue to drop and things are not so good. Bicarbonates help buffer it. Where does acid come from in soil is something you might ask. This is hopefully something new for you. We talked a little bit about it in Plant Science 2, but let's continue. Basically, plants produce protons. This picture, you're seeing a proton that leaves the root and it goes over to the soil colloid and it knocks a nutrient off. Let's say it takes the potassium and it absorbs the potassium, so it exchanges. It's like a barter system. And the other thing that happens with roots is when they're growing rapidly, roots produce actually quite a bit of carbon dioxide. We often think of plants consuming carbon dioxide, right? That's in the leaves, but in the roots they actually produce CO2. And that CO2 is very water soluble. It goes into the water that's in the soil and produces carbonic acid, which is carbonate, not bicarbonate, it's just carbonate, and a proton. So by its very nature, when plants are growing and happy and healthy, they acidify the soil. Okay? So they actually themselves contribute to the acidification of the soil. And we have to make sure that they don't overdo it. And this is especially important when we're talking about hydroponics, where we're recirculating a known solution all the time. So some soils become acidic when the root is dumping out protons, and others become alkaline, depending on the type of nutrient. This is an important fact. We'll come back to this a few times. If you notice between these two statements, there's a key difference. These all have a negative charge, and these all have positive charges, right? So what does that mean? That means that nutrients that are high in potassium, ammonia, magnesium, basically anything with a positive charge, when there's lots of those nutrients in the fertilizer, you know you're going to have acidic soil. That can be a good thing, right? Let's say you're trying to grow blueberries. You're going to use a fertilizer that's going to encourage the plants to pump out acid because blueberries love acidic soil. So by choosing the right fertilizer, you're contributing to the success of that crop. Whereas when you feed crops negative charged ions like nitrate or chlorides, possibly phosphates, you're going to raise the pH of the soil. So that's an important thing to consider when you're designing a fertilizer or when you're choosing a fertilizer. Okay, so charge for charge. If your root is absorbing a positive charge, it's going to put out a positive charge. What's the positive charge? It's a proton. If your root is absorbing a negative charge, it's, say, a nitrate, and it's going to produce a hydroxyl, an OH, which is negative. So this is acid, and this is basic. So the trick is to design your fertilizer so that it's balanced, essentially, right? We want it to be balanced at around the right pH. I can't go back, but typically plants like to be anywhere in the pH range of as acidic typically is 5 to 6.5 to 6, in that range. They tend to be slightly on the acidic side. There's not many plants that like alkaline soil, very few. So this is probably the most critical nutrient that we have as growers to control pH, and that is your form of nitrogen. There's a link in this week's class folder to a document produced by Cornell University which describes nitrogen. I would encourage you to read it. It's really useful. But essentially, you have two common forms of nitrogen in the greenhouse world. We have ammonium and we have nitrate. Now, urea, which is used in field production because they go through so much, it's cheaper. There's actually enzymes in the soil from dead bacteria that quickly convert it to ammonium naturally. So we'll just treat it as these two, ammonium and nitrate. So when you have fertilizer that's high in ammonium, it's going to encourage acidic production from the roots. If we have nutrients that are high in nitrate, we're going to have a more alkaline soil condition. So typically your fertilizer has to balance the two. And this is a really important statement here. Fertilizers themselves are not acidic or alkaline. Not much. It's essentially what has to happen is the plants have to act on it in order for it to become acidic or alkaline. That's why we often use the term potential acidity, because we're waiting for the plants to start feeding on it. Once they feed on it and they react, either microorganisms in the soil which react to it or the roots, then the pH changes. So if we have a situation where, for example, you're using well water, let's say you're running at a farm, an organic farm, and it's got really alkaline, hard water in the well. That's going to be a problem for your plants. So you're going to look for fertilizers that are high in ammonium. And fortunately for you in the organic world, a lot of organic fertilizers are pretty much ammonium based. There's not a lot of nitrate available to organic fertilizers. So typically organic farmers struggle with their nitrogen form. But anyways, whereas if you have an acidic soil, which is unlikely, then you would use more nitrates. This is a chart showing, remember what I mentioned here, potential acidity or basicity. So A stands for acid and B stands for base. So this is high pH. This is low pH, acid. So when you add something like ammonium sulfate, that's the ultimate. It has a very high acidity to it. If you want to know what the number means, this is typically tons of bicarbonate required to neutralize 1 ton. So if you put 1 ton of ammonium sulfate into a suitable solution, in order to bring the pH back to pH 7, so neutral, you would have to add 2.2 tons of ammonium sulfate. 2.2 tons of bicarbonate to bring the pH back. So it's very acidic. Ammonium sulfate, because it is so acidic, is the fertilizer of choice for crops that like acidic soil, like blueberries and rhododendrons, for example. Down here, 20-0-20, look at that, 0. This is a perfectly balanced pH fertilizer. Mind you, you can't use it alone because it's missing phosphorus. This would be a companion fertilizer to something else. And then move down here to, say, 15-0-15, or what we use at the college, 14-0-14 is not here. Those are basic fertilizers, so they will raise the pH in time. So from a practical perspective, and what you'll see at the college, we use different fertilizers at the college. I don't know, I'm not the grower, it doesn't matter. 20-10-20 and 15-0-15 is often used in the industry, or 28-20 and 14-0-14. Those formulations are such that one acidifies and the other raises the pH. And then they will alter, so they'll do 1 week of a particular fertilizer, switch to another one the next week, and then on the 3rd week, they'll use Epsom salts because there's not enough magnesium in these fertilizers. And they just repeat. So typically your 20-10-20 is going to acidify 1 week, and then you bring the pH back up with 15-0-15, and magnesium sulfate's neutral, and then you repeat the cycle. Now this is not hydroponics, this would be growing ornamentals like poinsettias, for example. It also has the benefit of the 14-0-14 has calcium in it, calcium nitrate, so that's how you also get your calcium for your crop. But if you choose correctly, your fertilizer program will have the pH stay pretty stable in your soil. And the reason you can go 1 week this, 1 week the other is because in the case of growing in soil, the soil buffers it so the fluctuation is not so drastic. Unlike hydroponics, where within an hour or two the pH has changed dramatically, you could kill your crop. So it's much more tightly controlled. So NPK, nitrogen, phosphorus, potassium ratios, they are specifically percentages. We've covered this in plant science too. This is just a repeat. But there are some very common rules that you'll probably have observed. And that is that, nitrogen and potassium are often in a 1-to-1 ratio, right? So we have 20-0-20, 28-20. The first and last numbers are almost always very similar. As far as phosphorus, the middle number, it's typically anywhere from 2-to-1 to 4-to-1 for nitrogen to phosphorus. So plants don't need a lot of phosphorus. Traditionally, at least a quarter of the nitrogen in terms of quantity. So why does triple 20 exist? That's a good question. Triple 20 is actually kind of a high polluting fertilizer, but it does evoke a rapid response from plants, so it's still used if a grower is behind schedule. The type of nitrogen that you use as a fertilizer has an impact on how plants grow as well. The form of nitrogen, so we talked about ammonium or ammonical versus nitrogen or nitrate right down here. Typically, if it's in the ammonical form or ammonium, we tend to get what we call soft, lush growth. So sometimes people think this looks really good. For example, triple 20 is high in ammonium. So if you feed a crop triple 20, the plant will look like it's growing rapidly and have beautiful, lush leaves. But what's actually happening is the cells that are growing are very large and have soft cell walls. And because the plant has a soft leaf, they often give off aromatics that attract insects. And because the cell walls are softer, it's easier for fungi to get a hold. So things like botrytis and mildew. So really, you want to try to avoid using too much ammonium fertilizer if you can. Whereas typically nitrate fertilizer produces a hard, well-toned plant that is drought resistant and pest resistant. And again, you might say, well, why don't we just use only nitrate? Well, remember, if you only use nitrate, we have a pH problem. So we have to use fertilizers that have enough ammonium in them so that we don't go too high in our pH range, but have most of their form in nitrate. That's why we use something like 2820 at the college, because it's got both nitrate and ammonium, but it's got more nitrate in it, so the plants don't get too soft. The other thing that is interesting about ammonium is plants typically ammonium is actually toxic to plants, but they can process it fairly quickly as long as they can move it to the leaves. Now on cold, clammy days, like in the fall and spring, plants can't necessarily move the ammonium very rapidly to the leaves, and so we end up with toxicity issues. So oftentimes we'll see nitrate fertilizers are considered cold weather, winter type fertilizers, and when you get into warmer weather, you can use more ammonium because the plants can move it more quickly and process it. So we have dark weather and we have finishers that are high in nitrate and low in ammonium. This is just a link. If you go to the regular PowerPoint, click on it, it takes you to the plant product website that see what happens if nothing happens. It takes you to a description of the fertilizer. I would encourage you to look at it and read it and see what it has to say. So if you were setting up a new crop, right, specifically hydroponics, you start with a water analysis. And that's to see what the alkalinity is. Remember, that's your bicarbonates. That's going to tell you also how much calcium, magnesium are in there, but it's going to tell you what the pH needs will be for your fertilizer. And if it's hard water in your well, you may already have quite a bit of calcium and magnesium, which means you can save money and you don't have to add as much gypsum, whatnot, to your fertilizer. You may not have to add any. You may have to add something to adjust the pH, but you might be okay. Depends on the water analysis. So there's no point in wasting money if you don't have to. This is an important statement here in this day and age of YouTube. Despite considerable gardening advice to the contrary, specific nutrients do not promote rooting or flowering. Now, a bunch of you are going to be like, oh, that's not true. Well, I'm sorry, man, it is. Flowering happens because a plant has reached a certain maturity level. It's developed enough, it has enough energy stored, and it's ready to flower. It's going to flower. Specifically phosphorus, which is often oversold to people because it promotes rooting and flowering. Let me explain how that came to be, and it might make more sense to you. Phosphorus typically in soil is limited in how plants can access it. And especially when the soil is cold and wet, plants struggle to extract the phosphorus from the soil. And so fertilizers that were typically sold for field production gardens or crops, they used higher phosphorus levels in the spring because plants would show purple tendencies and be stunted because the soil wasn't warm enough. And that was especially bad in a cold, wet spring. And then for some reason, people started making the association that high phosphorus levels are really important for young plants to grow. And so then they started buying it when they weren't growing in a cold, wet field, but in a greenhouse. So it's actually misguided and poorly understood. That isn't to say that phosphorus levels are not played with in the greenhouse, but they're not played with for reasons that you might think. For example, in a greenhouse, a grower may choose to actually limit phosphorus to purposely stunt young plants so that they're short and stout and they're easier to transplant with a machine. They don't get broken. Does that mean it's the best thing for the plant? Possibly not, but it achieves a purpose. Or let's say it's a grower that's selling young plants or plugs to other growers and they have to grow lots of these and ship them. they have to actually fit in the box. And so growers, again, will play with phosphorus levels to either shrink, or if they have to stretch, they'll add excess phosphorus. But as far as nutrients impacting flowering, the only thing that is true is adding too much nitrogen can actually confuse plants, and they may not flower. So they may have reached maturity, they may be ready to flower, but if you're still babying them with all kinds of wonderful nitrogen, they may just continue to produce vegetative growth. So oftentimes, and this is where another misunderstanding happens, fertilizers that are for the flowering stage look like they have high potassium levels and low nitrogen levels. But remember, the fertilizer ratios are just telling you what's in the bag. So if it's 5, 5, 10, it has 5% nitrogen, 5% phosphorus, and twice as much potassium to the nitrogen with a 10. What's really going on in that context is that a farmer may be wanting to make sure that the flowers kick into flower at a consistent time. So they withhold nitrogen by lowering the nitrogen content, and they usually just leave the potassium at the level it was before. They're not actually supplying excess. It just looks like they're supplying excess. But if you say you had 20, 10, 20, right? It would be like switching to 10, 10, 20. So you've left the potassium the same, but you've halved the amount of nitrogen. And that way the plants all at once say, hey, let's not produce as much vegetative growth, let's flower. Now you would only do this when the plants are developmentally ready. And right now is a really good time to see that happen, and that's growing fall mums. Because they reach a certain developmental stage and then they start forming buds. Now they've already started, but the growers would have switched at that point to a low nitrogen formed fertilizer with the same levels of potassium. So the plants can continue to produce flowers, but the mums don't get too bushy and overgrow and become giant behemoths that don't fit in the pot or bag. So for all those people who think that supplying huge amounts of potassium is going to increase their yields and increase the number of buds, it's a lie. You're just being fed a lie from people who don't understand plant chemistry. Sorry about that. We could talk more in the greenhouse because I'm sure a bunch of you right now want to talk to me. Phosphorus comes in different forms: ammonium phosphate, urea phosphate, and phosphoric acid. Typically phosphorus, you're looking at 2-to-1 nitrogen to phosphorus. Again, 20-10-20, classic. It's about half the nitrogen is phosphorus in content-wise. So adding excess phosphorus, the only thing it will do is stretch a crop. And the only time I've ever seen this done was with cut flowers that were trying to get longer stem lengths because they get paid by the length, and that way they could quickly produce stretched cuts. I have seen it used occasionally with plugs that were too short for maybe a growth regulator error, but adding huge amounts of phosphorus, not going to do anything for you. Nothing good. Potassium, this is one of the most underrated nutrients and is really critical. This is why when I started off talking about potash, I was trying to emphasize how important it is. Remember, it's often on a 1-to-1 basis with nitrogen as far as plants are concerned. So they need a lot of it. And almost the entire role of potassium is really obscured because potassium doesn't play much of a role in DNA. It doesn't play a role in protein. It doesn't play a role in sugar, not significant. What does potassium do? All it really does is create osmotic gradients. And the classic osmotic gradient that all plants need is opening and closing their stomata. So remember those pores on the leaves? They only open by having potassium pumped in, which creates an osmotic gradient, makes them swell, and opens the pore. If you can't open that pore, the plant can't breathe. That's like you holding your breath. So if your tree or plant runs out of potassium, guess what? It can't open its stomata. If it can't open its stomata, it can't breathe. That can't be good, right? So that simple role, it seems like, oh, it's just stomata. But think about it. If you had to hold your breath, how long are you going to last? So potassium is absolutely critical to make sure you have enough. And the nice thing about potassium is from a growing perspective, it's actually really hard to oversupply other than wasting money, But only time you see potassium where growers go a little bonkers with potassium is once again in field production, growing things like carrots and gourds and whatnot. When farmers are getting close to harvesting their crop, they often put out what's called crop boost, which is a high potassium content fertilizer. And what does that do? How does that boost the crop? Here's how it does. It makes sure that plants have excess potassium because they will take up extra and store it in their vacuole. And potassium, remember, potassium creates turgidity. So if you are a farmer and you're selling carrots and you're going to send them to the market in trucks, in boxes, in bags, they're bouncing down the highway, and then they get thrown on the shelf at the grocery store, and they get thrown in the buggy. If those produce don't have enough potassium, they don't have enough osmotic potential, they lose their turgidity and they become soft. When they become soft, they have a shorter shelf life and they bruise more quickly. So that crop booster is really just to extend shelf life, make them look better and store better and not bruise. Calcium, magnesium, we're almost done here. Dolomitic lime is a common source. Limestone, often it's in irrigation water if you're using groundwater. If you're using rainwater, there's not much in it. Be aware of that. So sometimes people have a pond on their farm, but if it's not fed with groundwater, it's just rainwater, typically it has very little calcium. We get calcium from fertilizer like calcium nitrate, which is a common one. Magnesium sulfate has some calcium in it. But, you know, lots of different places to get it. It's a really important nutrient as well. As far as ratios go, and this is an important one, calcium and magnesium are important. They're not always listed on a fertilizer bag, but they often are. So if you see a fertilizer bag that has more than 3 numbers, so let's say it's 5, 15, 5, 15, 5, 15, 3, 1. That means the 3-1 means it has 3% calcium and 1% magnesium. So fertilizers that are incomplete that you need to add Epsom salts to don't have 5 numbers, they have 3 numbers. So that's your hint that you have to add Epsom salts in your fertilizer or you're going to have calcium magnesium problems. So remember, the ratio of calcium to magnesium is typically anywhere from 3-1 to 5-1. In other words, if you start adding gobsmacks amount of magnesium, you're going to interfere because they're antagonistic. They antagonize each other. You're going to interfere with calcium, and your plant's going to have a lot of calcium problems. So if you go crazy with the Epsom salts, expect to see calcium deficiencies in your plant. pH, we'll talk a little bit as we go through. You already had an introduction to that in plant science too, but you know, if you have your pH too high, plants struggle to absorb them. Or too low even. What am I trying to say here? Yes, I've already mentioned this, but calcium and magnesium are frequently omitted from fertilizers. So keep that in mind. Some farmers, even ones who've been at it for years, don't realize that they need more Epsom salts or dolomitic lime. Now, if you're growing with a commercially prepared peat moss, they actually add dolomitic lime to the peat moss to buffer out the acidity of the peat. And that charge of dolomitic lime often will get you through the first few weeks of your crop. But after that, it's gone and you need to supplement. If it's a quick crop, you might be okay. But if it's a longer crop, you're going to have to supplement. So, and there's the 5. So here's the 15, 5, 15, 5, 2. So it's got 5% calcium, 2% magnesium. So it satisfies the 3-1 to 5-1 ratio. So, lastly, micronutrients. Micronutrients are all the minerals I was talking about in the very beginning, the trace elements, things like boron, molybdenum, iron, silica. Those things are all added to nutrient solutions as what we call micronutrient solutions. And they're often in a chelated form. What does chelated mean? This is a picture of a chelating molecule. And if you look at it, it looks kind of like, say, this is the metal ion of interest here. Let's say it's iron. It's suspended, like trapped in a three-dimensional matrix. And that is really critical to make sure that those minerals are accessible to a plant. Think about it like this. Metals are very reactive molecules, which means they don't like being on their own. They react to other chemicals very quickly. And once they've reacted, they may not be available anymore to the plant. So the classic, oh, you have an iron deficiency in your crop, throw a rusty nail in your nutrient solution and that'll solve your iron problem. Well, that's not true, because as soon as iron rusts or oxidizes, it's changed into a different chemical form the plant can't use. So that's completely useless. All you're doing is putting a rusty nail in your water. Iron has to be protected, as most metals do, in some sort of structure. And these are links here to different types of chelating agents. I believe EDDHA is the best one because it has the broadest pH range that it's effective at. EDTA is the most common. If you look at your cereal box, you'll see that there's EDTA in it with vitamins for us. So when us as humans, we need iron in our diet, it's often in some sort of chelated form. But DPTA is pretty good. EDDHA is the best. EDTA is the least effective. It also doesn't break down rapidly. So in hydroponic solutions, it starts to increase in concentration if you don't change your water, and it actually becomes toxic to the plants. So be very careful about that. It can also be bad for fish in aquaponics. So EDDHA is your best bet.